Good morning, class. All right, today we are starting Unit 1, Science Skills, Section 1, Measurements. So hopefully this will be mostly a review for everybody in the room, but there are things that should be gone over every year. So I've got a lot of information to cover, but I'll try to go through each of these topics pretty quickly, at least for the video. We can talk about them in more depth in class. But let's get started. So the first thing we're going to see here is a beautiful deck that I helped build as part of a carpentry crew a few years ago. And there's a great story that goes along with this. Moral of the story is measurements are hard, and they're not always perfect. So hopefully we'll get to do that story in class, but if not, you can read through and try to pick out which one I am. Am I Ryan or am I Vinny? We'll talk about it in class. Okay, so measurements are hard. They're not always taken perfectly, and it's important to remember that measurements are not perfect. So there is two things that can go awry in measurements, accuracy and precision. So accuracy is how close a measurement is to the correct value. So if you use the analogy of a dartboard and a bullseye, this would be a highly accurate measurement because all the measurements are centered on the correct value, the center of the bullseye. This third one would also be a high accuracy or highly accurate measurements because if you took the average of all these measurements, they would be centered roughly on that bullseye, which makes them accurate. So accurate means that you're taking measurements dependably and repeatedly around the correct answer. Now, it's important to realize that every time you take a measurement, it's never 100% accurate. You're never going to be perfect. We could have everybody in this room measure the height of the desk and we would get 15 different numbers. And that's okay, and that's normal. So this is still considered highly accurate because the numbers are centered around the correct value. So highly accurate, highly accurate. Now what's the difference between them? The difference really is the measuring device. So if I were to measure the height of, actually let's do the length of the height of my coffee cup. If I were to measure the height of my coffee cup with a caliper, a dial caliper, I would have very precise numbers. So it would look like this. I would know the height of my coffee cup to within a few thousandths of an inch or a few hundredths of a centimeter. And that would be great. Now, what if I measured the height with a tape measure? Now I'm going to get a little less accuracy, a little less precision, but hopefully the same accuracy. So I would know if I used a tape measure, maybe plus or minus 1 millimeter, half a centimeter, something like that. But with a micrometer or a dial caliper, I would know that to plus or minus 0.001 millimeter, something like that. So your precision is really driven upon your measuring device. So that's the degree of exactness. If you have more tick marks on your measuring device, you have more precision to measure with. Accuracy is if you have the correct value or not. So if you have a very precise dial caliper, but it is set up incorrectly, it could be very precise but inaccurate, which would be this scenario right here. So you having very precision numbers, but they're just not correct. That can happen if your measuring tool goes out of whack. So for most of the time, we want this right here. High accuracy, high precision, but sometimes we want high accuracy, low precision. Sometimes, if we go back to the deck analogy, I don't need to know all of my measurements on a deck to plus or minus 0.001 millimeters. If I were to try to keep that type of precision, your deck would cost way too much money. So you would want high accuracy, low precision while making a deck. If you were making an iPhone, you'd want high accuracy, high precision, because plus or minus 1 millimeter on your screen size is going to make a difference on your iPhone. Plus or minus 1 millimeter on a deck, you'll never even notice. So accuracy and precision, there are two important things with measurements. It's important to know both of them. Precision will go into how we measure and significant figures, which is a lot about what we're going to talk about today. All right, moving forward. How to take a proper measurement. So look at the screen. Let's start here and decide what you think that measurement should be. If you were to properly take that measurement, what would it be? I'll give you a couple seconds. Let's assume this scales centimeters. So usually in class I get a range of numbers, something like 29 centimeters, 29.2 centimeters, maybe even 29.25 centimeters. All right. Now, a lot of times I would say, I'd say all of those are probably correct. There's one proper way to take that measurement, so technically there is one correct answer here. So the way to properly take a measurement is you measure to the amount of tick marks you have, and then you estimate one digit. So we know it's between 29 and 30. So that's what we know, and then we estimate one more digit. So I'm going to say it's about 29.2. So that would be your correct measurement. Because you can tell it's not 29.5, it's not 29.7, it's about 29.2. And that's as accurate as we can get with this scale. So that's the precision I can get with this scale. All right, good. So that's a proper measurement. These two would be considered incorrect. Now let's look at this one. What would be this measurement? Write up some common ones that people would give. 29.2, 29.25. Maybe even 29.251 centimeters. Which one's the correct one? All right, so we're going to measure to what we know and estimate one digit. I know it is 29.2. It's between 29.2 and 0.3, according to our scale. And I'm going to estimate one more, so we'll say 29.25. You could probably say 29.24, something like that. All those would probably be fine. So that's the correct measurement for that scale. You can see this one has more precision than this one, which is fine. Depends on what you need it for. All right. All this brings us to significant figures. Because when we are looking at these numbers, it's all well and good. This one is more precise than that one. But how do we go forward with that? And how we go forward with that is significant figures. This has 3 significant figures, and this one has 4 significant figures. So it has more precision. So we need to track significant figures. We need to keep it in our calculations. We need to pay attention to it all year long. So significant figures are a convention used to indicate precision upon measuring. Most things in science are based on measurements. So we need to know our precision that they were measured with. They're dependent on your measuring device because that's where we get our precision. And if you use proper measurements, it's going to include all the digits that can be measured plus one estimated digit. That's just proper measuring technique. Okay, so let's take some measurements. This is, I'll give you a 0 level here. 0 and 1,000. So we know this. What we know is tick marks to 0 and 1,000. So we could estimate one more between that. So that would be, I'm going to call this 500 milliliters. And that's correct. So in this, we have one significant figure. There's 5. We know it to the hundreds column. So we only know that. So this would have one significant figure. We come over here. Again, this measurement looks like 500, but this one has a bit more precision, right? So I know it to the hundreds column. That means I can estimate it to the tens column. So that means that this digit is significant, and we have precision to that digit, but we also have precision to the tens column. I know it's not 550, and I know it's not 450. So I can estimate it to be 500 exactly, and I know it to that tens column. So that means this one would have two significant figures. Okay, now we come down here. Again, our measurement is 500. I know it to the hundreds. I know it to the tenths, because now we have these tick marks on the tens column. That means I can estimate the ones column. So this has precision, and I can estimate that one. There's my estimated digit. So this has 3 sig figs. Here I got 500 again. Okay, I know it to the hundreds. I know it to the tens. And now I know it to the ones column. So I can estimate one more. So now I can add in one of these. I know it's not 500.5 because that would be up here. And I know it's not 499.5 because that would be down here. So I know it to the ones and I can estimate the tenths. So that means that this one, precision, and here's my estimated column. So this would have 4 significant figures. Okay, beautiful. So the question is, if you were to see a measurement of 500, how would you know how much precision it has? And you would know by how many significant figures it had. So these two would have to be shown differently, and we'll see this in a minute, to indicate there was more precision there. And we'll see what that means in a second. So we got to learn the rules around significant figures is what we mean by here. Because your significant figures tell you how much precision is in that measurement. Okay, significant figure rules. If you have non-zero digits, 24, 2 and 4 are non-zeros. They're not a zero. So that means they're significant. So anytime you see a number, 24, the 2 and the 4 are not zero, so they're considered significant. So you know, whoever took this measurement had accuracy or precision to this ones column. So that's what you know based on just looking at the number. Okay? So this has 2 significant figures because both digits are non-zero. Now, the zeros are where everything gets confusing. So let's look at there's going to be 4 of these significant figure rules. 3 of them have to do with the zeros. And one of them just says, if it's not a zero, it's significant. So the zeros are the tricky part. All right, let's look at our first case, 409. So non-zero number, that's significant. Non-zero number, that's significant. Now, if we were to take this measurement and we knew the precision to the ones column, would you also know the precision in the tens column? And the answer is, of course. So if you ever have a zero between 2 non-zeros, that's just going along for the ride, because that's a good number. Because you already showed you have precision to this ones column. So this has 3 significant digits, and you know its precision is to the ones column. So if you have a 0 between non-zeros, that goes along for the ride. All of those are significant. So you know you have precision to the ones column. All right, the next 2 are a little bit more confusing. And they both have to do with trailing zeros or preceding zeros. So let's look at this number, 0.80. Now, non-zero, so that is significant. The question is, don't pay attention to this one, we'll talk about that one next, but what about this one? So we have 0.80. Now, could you write this number as 0.8? And the answer is, of course you could. So somebody put that there for a reason. So they put that second 0 there for a reason, and they put it there because they know the precision to that hundredths column. So you should know that when you see it, and that means that is a significant figure. So you have precision to that column, the hundredths column. That's the only reason they put that 0 there. Otherwise, they just would have wrote 0.8 and would have been good. So anytime this is called a trailing 0 after the decimal. Trailing 0 on this side of the decimal is considered significant. And we'll see some examples to practice that. Okay, but there are other zeros. What if you have trailing zeros before the decimal? Not significant. You have to put those zeros in there to show that the number is 2300. So if you have a trailing 0 before the decimal, on this side of the decimal, that is considered not significant. So this would just have non-zero, non-zero, not a trailing 0 after the decimal, and not a 0 between two non-zeros, so those are just not significant. So only 2 sig figs there. We only know this precision to the hundreds column. All right, I'll come down here. 0.004, non-zero, significant. Now you have preceding zeros. Could you write that number without those preceding zeros? No, you have to show them there to show the number correctly. And they're not a trailing 0 after the decimal, and they're not between two non-zeros, so those are not significant. I always call these two sets of zeros. Preceding zeros are never considered significant, and then they're just like placeholding zeros. They just help you to write the number, but they don't actually add any importance to the number. So those are not significant. So it's better to practice these and just kind of see them in practice to get a handle of it. So let's do that. All right, let's identify our number of sig figs. Okay, non-zero, non-zero. Here we have trailing zeros on this side of the decimal. Not significant. So this one has 2 sig figs. Beautiful. Now we got 0.0012. All right, non-zero, non-zero. Preceding zeros are never significant. So again, 2 sig figs. Okay, 401, non-zero, non-zero. Anytime you have a 0 between 2 significant figures, you know this to the ones column, so that's just going to come along for the ride, right? So this one would have 3 sig figs. 12.80, okay, non-zero, non-zero, non-zero. And there's really 2 areas where you can have a 0 be significant. If it's between 2 significant figures, like here, then it's significant. Or if it's a trailing 0 on this side of the decimal. Significant. So those are your 2 cases where you're going to see a 0 be significant. Trailing 0 after decimal, significant. 0 between significant figures, significant. All right, let's look at this one, 0.00770, excuse me, 0.0770. So significant, significant. Trailing 0 after a decimal, again, that's good. Preceding zeros, never significant. So 3 sig figs here. Now the only one that might be a bit tricky would be something like this, 200.0. Okay, significant figure, right? Non-zero. Trailing 0 after decimal is significant, right? Now this one, it's not between 2 non-zeros, but it is between 2 significant figures. So those go along for the ride too. Because if you know it to the tenths, then you know it in the ones in the tens column as well, right? So this would have 4 sig figs. Beautiful. Let's keep going. Here's where things get tricky. We now have to do some calculations with these numbers. So the important part about sig figs is when you take your measurement, you're indicating your precision. And anytime you do a math operation with those numbers, you have to stay or keep track of that precision with each calculation. So anytime you add, subtract, multiply, divide, do anything to a number, you have to continue to have its precision follow through that calculation. So we're going to do two cases here, addition, subtraction, and then multiplication and division. Strangely enough, multiplication and division are very easy. Addition and subtraction are the ones that are trickier. All right, so let's look at these three numbers we are adding here. 101.25. So we know this one, it has precision all the way to this column, right? That's the tenths column, nope, hundredths column. If we look at this next number, it has precision to the tenths column. And then this third number we are adding, it has precision to the thousandth column. Now, when we add or subtract it, so we add these, it's important to remember this 3,536.2, that 0.2 is an estimated digit. So that could be 0.25, 0.15, easily, right? That's part of the estimation is we know it's not exactly that, but it looks close to that. So if we are not very certain on the tenths column here, then how could we go give an answer that we're very certain to the thousandth column? We can't, right? If we're not certain here in the tenths column, then we're certainly not certain here in the thousandth column, right? So this is your math answer. In math class, everything is perfect, and you can certainly keep that measurement there. But the difference between math and science is in math, they're just numbers. In science, they are measurements. So if there's a measurement, it has precision, and we can't go making up precision here. If this could be 0.15 or 0.25, then this could easily be higher or lower as well, correct? So what we do is you do the column of least significance, I always say. So if we know this to the hundredth, this to the tenth, and this to the thousandth, you align them by their decimal point, and whatever significant figure you identify that is most to the left. So you come to your number and you identify the significant figure most to the right. So that's why I underline this one, and this one. And then you identify in your answer the column that has one of the numbers you added up most to the left. So we have to round to that tenths column because we only know this number to the tenths. So that means we have to round to that as part of our answer. So your math answer would be to the thousandth, but your science answer has to be rounded to the tenths column. Make sense? So that's a little bit tricky. And you just got to kind of pay attention and make sure you kind of track it through. So let's do a few of these for practice. All right, so I'm going to add these three numbers together. And I'm going to start that by aligning them by the decimal point. So 25.4 plus 0.24 plus 8.91. And I'm going to examine all these numbers. I'm going to find out where they have precision to. So this has precision to the 10th column. This is the 100th and the 100th. So I already know I need to round my answer to this 10th column. All right, so let's add those up. We'll get a math number first. So we have 5, 34.55. Did I do that right? I am pro calculator, if you're wondering, because you don't make mistakes. So here's our math answer. Now we have to round this for science, and as we identified earlier, this number we only know to the tenths, so that means we have to round to the tenths. So our science answer would be 34.6. That is your correct answer, and that's what you'll be required to give for a correct answer throughout the year. All right. That doesn't seem that bad, right? Sometimes this can get annoying. So let's look at these two numbers, 3,000 plus 15. So let's do what we did over there. We'll align it by the decimal point first. So 3,000 plus 15. We'll go through, get our math answer first, just to be quick. So 3,015. I'm going to erase this just so I can align those columns a little better. That's our math answer, right? So in science, we needed to evaluate our significant figures and our precision. So we know this one, the first thing you do is identify where you know its precision to. We know that precision to the ones column. In this one, we only know our precision. This is our first significant figure, way back here. So that means we need to round our answer to the thousands column. So that means our answer would be 3,000 for science. And that is correct. So in science class, 3,000 plus 15 is 3,000. That's quite annoying. So if you wanted to know, or you wanted that to not be the case, say you wanted to know it to more precision, the answer is not just to make it 3,015. So if that bothers you that this 15 is being dropped, the answer is don't just keep it in. That's not the answer. The answer is you need to know this measurement more precisely. So if it bothers you that you have to round to the thousands column, that's okay. The solution to that is to take this measurement with more precision. If you were to take that measurement with precision all the way to the ones column, then you could know it to be 3,015. But you didn't, or the person did not. They only measured it to the thousands column. So that means we can only know this to the thousands column. So this could easily be 3,500 or 2,950. We don't know because of the precision of that measurement. So that's the way it works in science. All right, let's move on to multiplication and division. These are much easier. What you do is find out how many significant figures are in each number that you're multiplying or dividing, and your answer will have the same number of sig figs as the measurement with the smallest number of sig figs. So what does that mean? So this first number here has 5 significant figures, correct? This second number has 2 significant figures. So we know that our answer has to be the smaller of those 2 numbers. So our answer has to have 2 significant figures. So again, here's your math answer. And then here's your science answer. This goes much quicker. As you can imagine, you don't have to align them by decimal point or anything like that. You can just throw it in your calculator and round to the smaller number of significant figures. So let's practice that. All right, 25.4 plus 0.84. Many times I like to just figure out how many sig figs there first. So this has 3 sig figs, this has 2. So we know that our answer is going to have 2 sig figs, right? So we'll throw it in the calculator here. 25.4 times 0.84. We'll put down your math answer first, 21.336. Beautiful. That's your math answer. Your science answer has to be rounded to 2 sig figs, so your science answer will be 21. So here's math, here's science. Like I said before, you're expected to give answers with proper sig figs. all year long. Anytime you do a calculation, you got to know how to do this. It's not hard once you get used to it. You just got to get in the habit of doing it. All right, come down here. Bunch of preceding zeros. They don't mean anything. They're not significant. We got a non-zero, significant, trailing zero after the decimal, significant, 2 sig figs. So 987, all non-zero, all significant. We know our answer has to have the smaller of those two numbers, so 2. So 0.00020 times 987. Our math answer is 0.1974. Okay, what's our math answer? We got to round that to 2 sig figs. So 0.2. Here's where things get a little bit tricky. We need 2 sig figs in this, right? So how do I indicate that both this column and this column have precision? Because that's what we want to do, right? 0.20 shows both of those being significant, and that would be your correct answer. So we have indicated precision here just by including it. It follows our significant figure rules. So 0.20 has 2 sig figs. That's good. All right, here's a tricky one. 800 divided by 22. We're not really tricky, but it's a good highlight. So 36.36 repeating. Now let's look in, that's our math answer, right? Let's look at our sig figs. Significant, trailing zeros, before the decimal, not significant. So this has 1 significant figure. 22 has 2 significant figures. Now if we look at this measurement, 36.36 repeating. So that means it's 36.36.36.36.36 forever and always. That means it's infinitely precise. So when somebody puts this number down, they are indicating it is infinitely perfect. I don't know about you, but I've never heard of something being infinitely perfect, especially on a measurement or something a human did. So do not ever list an answer like this. So this is your math answer, but if we look at our 2 sig figs, 1 and 2, we know that this has to have 1 sig fig. So our science answer would be 40. Certainly not infinite precision there, and that's okay. If we wanted to know that to more precision, we could retake that 800 measurement, and we could know more precision. All right, not bad, right? Last thing we got to look at is scientific notation. And the reason we have to know this is because of that 500 measurement we talked about before. So remember we had 500 milliliters. And then we had 500 milliliters with 2 sig figs. So here's 1, here's 2. And then we had 500 milliliters with 3 sig figs. Now, we all know that scientific notation is very helpful for something that's very large, like numbers that are very big, or numbers that are very small. And that's true. We'll continue to use it for that reason. But it also can be used to identify the number of significant figures. So if I wrote those 3 measurements, you would have no idea how many significant figures they would have. Actually, you would. You would know that they had 1. So if you just wrote it like this, that shows 1 sig fig. If you have 2 significant figures, you have to do something to show that. And a good way to do that is to use scientific notation. So I have to show that this 0 is significant. So if you turn it into scientific notation, you can do that. So I'll do this quickly because hopefully you know how to use scientific notation at this point. But what you do is you take your decimal point and you move it to get your base number. And that base number has to be between 1 and 10. So 5.0 is between 1 and 10. You notice I'm bringing over 5.0 because that is a significant figure. So we're going to bring that over. And then you do times 10. The number of swoops is your exponent, so we moved it 2 times. And we also got to decide if that's positive or negative. We started with a big number, so that means that your exponent is positive. If we started with a small number, your exponent would be negative. There's also rules about like if you move left, this is positive. If you move right, it's negative. I would tell you to not try to remember that because you'll forget it and or flip-flop it in your brain, or at least I do. So it's just better to know that if it's a big number, it has to be a positive exponent. If you have a small number smaller than 1, you have a negative exponent. That's how I remember. All right, so this shows 2 sig figs. So we're game on here, right? So that's good. We have just used scientific notation to show an additional significant figure. Could we use it to show 3? Sure, we would just label our base number as 5.00 times 10 to the positive 2. Beautiful. That shows all 3 of those are significant because these are trailing zeros after decimal. All right, beautiful. Let's do one small number just to show you. All right, so here's our number. I want to change that significant into scientific notation. Again, the first thing you're going to do is move your decimal to get a number, a base number, which is this thing right here, between 1 and 10. So I'm going to move it 1, 2, 3, 4 places. So I get 5.80. I brought that 0 with it because that's significant here, and I want to keep that significance going. And we are times 10. Again, we started with a small number, so we have to have a negative here, and we have 1, 2, 3, 4 swoops. Hopefully I'm not blowing your mind with scientific notation. You guys should know that already. So 5.80 times 10 to the minus 4th. We have shown 3 significant figures, and we have shown it in correct scientific notation. All right. Went over a lot today. Nothing too hard, hopefully. We looked at accuracy versus precision. Accuracy is how correct a number is, and this is the degree of exactness with which you measured it. We learned how to correctly measure. So you measure to your tick marks plus 1 estimated value. We learned that significant figures indicate precision, and we learned the 4 rules to identify how many significant figures there are. We learned math operations with sig figs. Addition, subtraction is one rule. Multiplication and division is the other rule. And then we briefly went over scientific notation, which I hope you already know. All right, glorious. I'll see you guys in